All right, so welcome back. Our next speaker is Arushi Nath, and she'll talk to us about integrating sparse and dense photometry methods for improved asteroid property analysis. Come on up, Arushi.
Thank you. Hello, everyone. It's great to be back in person at the Ontario Science Centre. My name is Arushi, and I'm a grade 9 student. Today, I'll be talking about a project I made where I combined sparse photometry with dense photometry to learn more about asteroids. So it's really impressive to say that even up to this day, we're still discovering hundreds of near Earth asteroids every month. Just last month, more than 180 asteroids were discovered. And we've started to get better with tracking these asteroids, detecting dimmer asteroids, and we've even started to get better with detecting asteroids before they impact with the Earth. For example, in January of this year, there was a small 1 meter asteroid which was about to impact the Earth. Of course, these are small asteroids, so they don't cause harm, and most of them burn up in the atmosphere. But we've started to be able to detect them before they actually impact. Actually, a citizen scientist, Christian, from Hungary, was the one who discovered the asteroid just 3 hours before it entered the atmosphere. And this was only the eighth asteroid to have been discovered before. And since we've gotten so good at tracking these asteroids, we were actually able to find exactly where it would land as different citizen scientists across the world started tracking the asteroids. And we were able to find the meteorite of the asteroid, which was pretty cool. And this is actually what my project is all about. What I'll be talking about is how to learn more about these asteroids. Because let's say we're not able to find a meteorite when it enters the Earth? Or what if everything burns up in the atmosphere? How can we still learn about the physical properties of these asteroids? So I'll start off by talking about a very simple concept. It's called the phase angle. So this is simply the angle between you, the observer, the asteroid, and the sun. And this angle tells a lot about the asteroid. And you could be standing anywhere. You could be on the Earth, you could be on a spacecraft. And the interesting thing about this is let's say the observer is on the Earth. We know that the Earth is always orbiting around the sun, which causes changes to the phase angle. But at the same time, the asteroid is also orbiting around the sun, which causes even more changes. So, what can this phase angle actually tell us? Well, as the phase angle comes closer to zero, we observe what is called the opposition. And I'm going to show you a short video which actually explains what happens during the opposition. So what you will see here is a moon of Mars called Phobos, and this is a video that's been taken from a Mars orbiter, and you will see what happens to the asteroid as it comes closer to opposition. So really look for what changes you can find. And on the right of this, you will also see basically how the phase angle is changing. So you can match it with what you see. So you can see the asteroid is slowly coming closer. The phase angle is slowly becoming smaller. Um, and you can see that the asteroid, there was a huge surge in the brightness as it came right at the zero phase angle. And you can see as the phase angle is becoming bigger again, the asteroid starts to become dimmer. So let me just go to the next slide here. Perfect. So what exactly was what you just saw? So you saw a huge surge in the brightness of this moon right during the opposition. And this is caused by two different effects. One is the shadow's disappearance. So of course, this is an object, there's many bumps, there's many craters, and these cause shadows on the surface of the asteroid. But when the sun is directly behind the asteroid, then the shadows will disappear, causing a huge increase in the brightness of the asteroid. At the same time, most of these asteroids have very rough surfaces, which causes the light to scatter as it reflects off the asteroid. And sometimes when this light scatters, it basically interferes constructively, causing an actual increase in the brightness of the asteroid. So, what exactly is this surge? So, this surge can be observed via what we call the phase curve. And this is a curve where if you plot the phase angle on the x-axis and the reduced magnitude on the y-axis. So what is the reduced magnitude? This is simply the magnitude of the asteroid with all other changes accounted for, like changes in heliocentric distance, changes in geocentric distance. So the only change in the brightness that you're observing is because of the phase angle. So you can see between the phase angles of 0 and 5, there is that brightness surge that's very obviously visible. And this is what we call, basically the surge in brightness is measured by what we call the slope parameter. And this slope parameter is very important for determining physical properties of the asteroids, which I'll talk about a bit later. And one thing that this phase curve also gives is if you look at the zero phase angle, whatever brightness reduced magnitude value you will see there actually refers to the absolute magnitude of the asteroid, because absolute magnitude is simply when there's a zero phase angle and where unity distances have already been accounted for. But after the 5-degree phase angle, from 5 to 25 degrees roughly, you will see that the line becomes relatively linear. And this is what we call the phase coefficient. And this is where basically the line becomes linear. And this can also give additional physical properties about the asteroid. So how exactly do we use this phase curve to find the physical properties? Well, the first thing is absolute magnitude, which I just talked about. So this is where the phase angle is 0, and there's a simple formula we can use, which uses the reduced magnitude to basically find um, this absolute magnitude. And the important thing it uses is the g, or the slope parameter, which I just talked about before. Second, to find the geometric albedo, this is where you use the linear slope that you see after. And one thing to note about this linear slope is that it can only be accurately determined once you have an accurate g slope. And this really causes us to think that we really need these important phase angles, these smaller phase angles of 0 to 5 degrees, to be able to accurately determine the whole phase curve. And finally, we can also determine the size from this phase curve just using the absolute magnitude and geometric albedo. So here the problem comes along. Because mostly you would think of using dense observations, like just taking observations from your own telescope to be able to observe this asteroid and find its magnitude. But the thing with this is while these time series measurements are very good for like finding rotation period of the asteroid, orbital period of the asteroid, where all of these clumps of data is really necessary, it doesn't really help us with the phase curve. Because in the phase curve, you need observations of the asteroid at different phase angles, which dense photometry simply does not give. So that's where I turn to sparse photometry. So this is taken from sky surveys, and this is basically time series data, but it's not continuous. So maybe one observation every couple of months. And the good thing is with this is we get to explore all the different phase angles of the asteroid. So by combining dense and sparse photometry, we would be able to get all of the physical properties of this asteroid. So how did I go about getting sparse photometry? Well, for here I used sky surveys. So one of the ones I used is the Gaia sky survey, and that's just Gaia is a spacecraft that's always orbiting around. And this Gaia Space Telescope has two telescopes, and it takes its measurements in the G magnitude. And this telescope is very good, and it gives us a huge range of phase angles from 10 degrees all the way to 30 degrees. But as I mentioned before, we also need the small phase angles. So while this is great for the linear part, we would also need more for the beginning part. So to get these Gaia observations, I simply used their database, where I was able to basically get the MPC code of the asteroid, and for each MPC code, I was able to get the date the observation was taken, as well as the magnitude I was getting and the magnitude error. So this would allow me to give me all the parameters I would need to get the magnitude and create a phase curve. So how many observations does Gaia take of each asteroid? This is where the problem comes along, because you can see as not many asteroids have more than 50 or 60 observations, and even below it's slightly more rare. And the thing is, we need a lot of observations to create a phase curve. So I used a second sky survey. This is the Atlas Sky Survey. So this is a ground-based telescope, and It's a 0.5 meter aperture telescope, so slightly smaller. But the good thing about this is it observes all phase angles, so the small phase angles as well as the big phase angles, which is exactly what we need. So to do this, I used the Atlas forced photometry pipeline, which I could input the MPC code I wanted or the asteroid I wanted, and it would give me all of the time series magnitudes that it had collected of this asteroid. And finally, I used this Wiki Transient Facility or ZTF telescope, and this is another ground telescope, and it actually scans the whole northern hemisphere every 2 days. And the great thing about this telescope is once again, it gave all phase angles, which was perfect because it would allow me to get everything I needed. So once I had all of these sparse observations, um, I decided to combine them with dense observations. So this, in particular, I was looking at a specific asteroid in this case called Didymos. Many of you guys must have heard in 2022, NASA launched its mission, its Double Asteroid Redirection Test mission, which was aimed at crashing into the moonlet of this asteroid to basically for a planetary defense test, because their goal was to change the orbital period. And I thought, why not use this asteroid as a test? So I collected sparse observations. In this case, I used the ZTF telescope. It's important to note that this asteroid was unfortunately too faint to be observed by the Gaia sky-based survey. And in addition, I got a few observations from the Asteroid Light Curve database, or ALCDEF, and this would give me the dense observations I need. So here you can see is the phase curve of Didymos. So it's from about 3 degrees to 20 degrees when talking about phase angle. And you can see that the triangle shapes here are all the sparse readings I've got, and the circles are all the dense readings I've got. And this allowed me to create the phase curve and basically allowed me to get the H and G values. So these were very important physical properties I was able to get, and it allowed me to get many parameters. First, I was able to find the absolute magnitude of Didymos using the formula I earlier mentioned, and I found it to be 18.14 magnitude. And this was using the G, so the opposition part of the curve. Second, I was able to find the geometric albedo of Didymos. This was using the linear part of the curve, so from about 5 to 20 degrees. And I found the geometric albedo to be 0.14. Then finally, using both the absolute magnitude and the geometric albedo of the asteroid, I was able to determine the size of Didymos, and I found it to be 840 meters in diameter. Um, but this geometric albedo is very interesting because geometric albedo, as you probably know, is basically shows how reflective the asteroid is on a scale from 0 to 1. And but this is not all it gives. It can also give so many more physical properties about the asteroid. In particular, I was looking at the composition because different types of asteroids with different compositions have different geometric albedo ranges. For example, asteroids who are carbonaceous will have a very low geometric albedo because they don't reflect much light, and this is normally below 0.1. Whereas metallic asteroids and silicate asteroids will have a higher geometric albedo as they reflect more light. So using this geometric albedo, I would be able to find the composition of the asteroid. So, knowing the albedo of Didymos was 0.14, I concluded that it was either S-type asteroid or an M-type asteroid. And as you can see on the right, this is an image from the Draco camera of the asteroid Didymos, and you can see that it definitely looks stony type, concluding that these results were correct. Next up, I'm going to talk about a different part. Now that I had the absolute magnitude, I had the albedo, I had everything else, what else could I get from the asteroid? So here I turned to the Lowell Minor Planet Services, where I was able to get the ephemerides of the asteroid. And this would be very useful for the next step, finding the rotation period of the asteroid. And this actually requires the G value of the asteroid that we calculated before. This would allow us to count for all types of offsets. The unity offsets, so the distance from the Earth, the distance from the Sun, as well as the phase angle. And this would allow us to basically turn from asteroid light curves where the change in brightness could be due to several reasons and actually give us light curves where the change in brightness was only due to the actual physical properties of the asteroid. And once we had this, then I could determine parameters like the rotation period of the asteroid. Because as asteroids rotate, they're irregular in shape for the most part. So their light curve produces two maximas and two minimas. And using my algorithm, I would be able to combine sparse photometry and dense photometry to basically combine these light curves and find the rotation period. And if the asteroid had a moonlet, as was the case with Didymos, I could simply subtract the rotation period from the main light curve, and then I would get information about the orbit of the moonlet. And I was able to find the rotation period to be 2.26 hours, and I was also able to find the orbital period. And actually, after NASA's DART impact, the orbital period of this asteroid reduced by 35 minutes, proving that the deflection was successful. And all my results were validated with external sources like NASA, and they validated very closely. And this proved that merging sparse photometry with dense photometry does give very accurate results for Didymos. And this is not yet over. I'm starting to expand my algorithm to work on several other asteroids. For example, here you can see the phase curves I constructed for three other asteroids: Eurybates, Themis, and Nyssa. And this is all done using multiple sparse datasets like Gaia, ZTF, Atlas, and then also combining them with dense photometry datasets like the Asteroid Light Curve database, so I could get the maximum physical properties possible. And you can see here I was able to find the albedo of these asteroids as well as their type or composition. And another thing I would like to do in the future is expand my photometry algorithms to find the composition, but find the composition more accurately. And how would I do that? This is using observations in multiple filters or multiple wavelengths. And this will require as well both dense and sparse photometry because different sparse surveys give the magnitude of different asteroids in different filters. And using my own dense observations or dense observations from databases, I can also find the asteroid in different filters. And this would allow me to find the composition. So you can see here, this is a preliminary analysis I've done with the 211 Isolda asteroid. And I was able to take the observations in four filters, R, G, B, and I, in the Johnson's filters, and calculate the absolute magnitude for each of the wavelengths. So more analysis on that to come up. And finally, I'm still looking to expand my algorithm to many more asteroids. In particular, I'm very interested in the near approach asteroids, so asteroids who are about to come very close to the Earth. And if anyone is interested, or if you know anyone who's interested in observing some of these asteroids, please let me know because I'm always looking for observations of these near Earth asteroids who are approaching. And I would like to finish off by sharing some outreach I've been doing in the past couple of months. Just last month in February, for the International Women in Science Day, I got to present to so many youths and parents and women about the importance of science and share a bit of my journey. In addition, I got to talk about the Royal Astronomical Society of Canada and how it shaped my interest for astronomy. In addition, just a few days ago, I was out in to, to talk about RASC at the Save the Ontario Place rally, which was held in Lynn Park. And in addition, a few months ago in December, I got the chance to speak to youth from all around the world, over 2,000 kids. And there I got to share my science journey and also mention the Royal Astronomical Society of Canada and all of the times I visited the observatory. So with that, thank you so much. I'd be happy to answer any questions.
Thank you very much, Arushi. Very impressive, as always. Well done.
Thank you.
We have one question here in the room.
Thank you. I noticed that most of your phase angles go to about 20 degrees. Would Might there be something interesting with phase angles greater than 20 degrees?
Yeah, well, phase angle 0 to 20 degrees is actually what gives the most important information. And after 20 degrees, there's not too many physical properties you can get.
Okay, any more questions in the room? Yes, oh, sorry. You go.
Is it true that Oumuamua had something to do with aliens?
Could you repeat that question?
Is it true that Oumuamua, the interstellar asteroid that passed us in 2017, they were doing similar measurements of brightness? What is your opinion on it?
I don't know too much about it, so I can't give an answer, but I'll definitely look into it and I can let you know later on.
All right, thank you.
Question over here.
Hi, great presentation. One question: when you analyze the wavelength of the asteroid, do you just get it like it's an S type, it's a C type, or you can know more about the composition?
Yeah, for sure. When you observe in multiple wavelengths, you're basically able to see how the brightness of the asteroid changes across wavelengths, which does give you information mainly about the composition. I don't believe there's anything else you can find from it, um, uh, at least to my knowledge, but maybe there is, but from what I can say, no.
Are you a grade 9 student?
Yes.
Okay, wow. I just thought that was maybe an old slide. That's amazing.
Thank you so much.
And we have one question online.
Zorkledge, yep.
We have one question online. It's, do you need to determine the shape of the asteroid to estimate the rotational period? That's from Guy Yanas.
Oh, that's a great question. And actually, you do not. To find the rotation period, all you need is the light curves of the asteroid. And once you determine the light curves, actually the amplitude of these light curves will give you information about how irregular this asteroid is, which can give you information about the shape. And but once you have the light curves, what you can do is you can take all of your light curves together and then combine them. What I did is I used a process which used root mean square error and congruent modulo, and where I was able to basically try fitting the light curves from periods 2 hours to, let's say, 10 hours, and then I found the one with the smallest root mean square error, and that gave me the rotation period. And while finding the shape of an asteroid is definitely a very interesting physical property that I would love to look into in the future, you do not need it for rotation period.
Any more questions in the room? None. Okay, well, thank you again, Arushi.
Thank you.
Great presentation.